Kia ora koutou, this is question 1e from this year's Level 3 Calculus exam. It's a parametric equations question and it involves finding the second derivative, which is pretty common, and then there's just a little twist at the end. So let's have a look. Okay, so we've got a curve defined by these equations. X is a quadratic and y is just 2t cubed. And we have to first find the points of any inflection on the curve, but we just want to find the points of inflection that are also stationary points. So we're going to find the points of inflection by setting the second derivative equal to 0, and then we're going to check to see if the first derivative is 0. And I've done a graph using GeoGebra, and I'll show you that at the very end of the video. So it's quite a boring question. I'm not going to go through slowly how to find the second derivative. I'm going to do it reasonably quickly. If you are just watching this near the start of 2026, go and find my other videos that teach you how to do the second derivative parametric, and then give you a bunch of examples to practice on. It's a skill that comes up often at like high merit excellence level in the Level 3 differentiation standard. Okay, right, let's go. We're going to start off by finding dx by dt and dy by dt. So dx by dt is going to be 6t plus 6. dy by dt is a very easy 6t squared. So dy by dx will be dy by dt times dt by dx, which gives us 6t squared over 6t plus 6. And we can clean that up and we get t squared divided by t plus 1. Now to find the second derivative, what we have to do is we're going to take that first derivative, this one, and we're going to differentiate it with respect to t, because that's all we can differentiate it with respect to directly. To get the with respect to x, we're going to use the chain rule. So that's how we do a second derivative with parametric. Okay, so you can see here I've got a quotient rule problem, hopefully staring out at you. So it's going to be t plus 1 squared times 2t times t plus 1 minus t squared. Cleaning that up will give us 2t squared minus t squared, so we get t squared plus 2t. If I were doing that in the exam, guys, I would definitely have an extra line of working in there. I just did that a little bit quickly then. So we've got this, and that means that now what we've got to do is times in this to get my points of inflection. So d squared y by dx squared will be t times t plus 2 over t plus 1 squared. And if we go back up, here is my dx by dt, back up here 6t plus 6. So it's going to be times 1 over 6t plus 6. So just one final cleanup step gives me t times t plus 2 over 6 t plus 1 cubed, and that equals 0 for a point of inflection. That means that all we have to do is to solve the numerator equaling 0. So t is equal to 0, or t is equal to -2. We go back to the start of the question to get our coordinates of the point, right? Because we've got t affecting x and t affecting y. So we're going to substitute into those two equations. Right, I'm going to do this quickly and just jump straight to the answer. When you do that substitute, oh no, I won't, I'll do it slowly. You get x is equal to 1. Oh, I'll just do it slowly. I think most of you probably not still watching anyway. There we go. X is equal to 3t squared plus 6t plus 1. Substituting in 0, we get x is equal to 1. And y is equal to 2t cubed. So y is equal to 0. So the point is 1, 0. Doing that same thing for t equals -2 gives me x is equal to 3 times 4 minus 12 plus 1. So this time x is 1 and y is equal to 2 times -8, which is -16. So my 2 points are 1 and 0, and 1, that's not right. 1 and 0. Oh, yeah, that is right. Yep, 1 and -16. So the reason why we're getting 2 different points with an x value of 1 is because we're doing something with implicit, right? So we don't have a function, we have a relationship between those two things. So it's totally fine to have an x value giving me two different y values, and you're going to see that in the graph in a minute. So far we've got the coordinates, and if you read the question, it says, you can assume that any inflection points found are actually inflection points. What they really mean is that we've found where the second derivative is 0, and we're just going to assume that they actually are inflection points. Now remember, an inflection point is where the concavity of the curve changes, and we can have inflection points where the gradient is 0 or where the gradient is not 0. If they're going to be a stationary point, then the gradient has to be 0. So what we've got to do with each of those points is we have to go back and we have to check whether dy by dx is equal to 0. So at x equals 1, 0, what matters is not the x value, it's the t value. We had t equals 0, so dy by dx is equal to t squared over t plus 1, and that equals 0. Therefore, 1, 0 is a point of inflection and a stationary point. Now, when we look at the other one, 1, negative 16, that's where we had t is equal to negative 2, and so dy by dx here will not be 0. It's going to be 4 over negative 1, which is negative 4. So 1, negative 16 is not a stationary point. Now, I don't know about you, but when I was doing this question, I was pretty curious to see actually what curves are we dealing with here. I think this is good revision for when you are first learning about points of inflection, about what's going on. So this is part of the graph. I've taken this from GeoGebra, and you can see here that this is my point at, let's see, have I got it right? Here's the point at 1, 0. So that's a point of inflection, and you can see that the gradient is 0, so it's a stationary point as well. And the other one is down here at 1, negative 16, and the concavity is changing, but the gradient is negative, which fits with what we got. If you're having trouble seeing that, it's quite subtle, but if you take a piece of paper and just cover up the screen, I'll try and do it with a ruler, because it kind of works. Just like divide your eye up so that you're looking at whether it's concave or not. So you can see the curvature is changing at that point, very, very slightly. It's just about linear over here. It's not if you look at the rest of the curve. All right, so that's that one done. I've got 2 more level 3 excellence questions to do. Going to try and do those today. If you've got any other questions that you want done, just chuck me an email and I'll try and YouTube them for you. Thanks for watching.